Hello, everyone. Today we are going to be in our calculus packets doing the last piece of it, which is the chain rule. First, we're going to start by checking the answers to the worksheet last night and then go from there. So if you haven't gotten the homework out from last night, get that out really quickly and let's check our answers. As a reminder, you can pause this video at any point if I'm going too quickly. So go ahead, check your answer to number one. We have two constant rates of change. So we get those two horizontal lines. First one positive, second one negative, and we don't have actual y values. So where you actually put your horizontal lines can change, but they should be about the same distance away from the x-axis since the positive rate of change and the negative rate of change seem to be about the same. Number two, same thing, we have three lines. So we have three constant rate of change. We have that negative rate of change, which is a pretty steep rate of change. And then we have 0, and then we have the positive rate of change. And again, where you put them can change depending, but you should have the positive horizontal line a little bit closer to the x-axis than the negative one, since the negative slope was a greater rate of change. Number three, take a look at that. So the slope is positive the entire time. Starts out with a very steep, very large positive rate of change and slowly kind of gets closer to 0. Number four, as we saw yesterday in class, when we have like that quadratic, it ends up looking like a linear derivative. And we have the slope is 0 at that maximum, which was like at about 2. And then we have the positive slope up to 2 and then negative slope. So we have our line looking like that. Number 5, same type of concept. We have anytime, again, there's a max and a min, we know that our slope is going to be 0, so we know that the derivative is going to be 0 right at that positive 1 and 3, and then we have that negative slope, positive slope, negative slope again, so there's that negative slope, positive slope, negative slope again. Number 6, we saw this one in class yesterday. We have, positive slope and then undefined right there, and then again a positive slope. We have, almost 0 and then becomes more steep. So we have almost 0 becomes greater and greater, and then undefined at 2, there's that vertical asymptote, and then we have starting out very steep slope that's slowly becoming more and more closer to 0. So the graph of our velocity function or the derivative ends up looking something like that. All right, and now 7 and 8, we were going backwards. So from the velocity function, can you make a sketch of the position function? So working backwards, we know that when the velocity is 0, we're going to have like a maximum or minimum. Since our velocity is negative here, positive here, that means that my position function is going to start with that negative slope until 2 and then change to a positive slope. So we have that reflected here. Negative slope changes to positive slope. And where you draw your minimum is can be completely different because we don't have any actual y values. So that's what this little comment here is talking about, is the vertical translation is fine because we don't know where exactly like the position function is. We just know that it will have that shape and we will have like that minimum at x is 2. Number 8, so we have for the velocity function are 3 constants. So between 0 and 2, we know we have a positive constant rate of change. Between 2 and 4, we know we have a negative constant rate of change. And then between 4 and 5, again, a positive. But we know that the positive rate of change between 0 and 2 is a greater rate of change than between 3 and 4. So that needs to be a greater rate of change than that. These look similar. Maybe this one's a little bit bigger than that one. So you could have made this part a little bit steeper, but I would say this and this look similar distance away from the x-axis, so similar steepness. We just have negative slope versus positive slope. So our graph should look something like that. All right. So go ahead and turn to the Calculus 9 derivative power rule, and we're going to start with a warm-up. Find the derivative of f of x equals 4 over x by evaluating using the definition of the derivative, which is the limit as h approaches 0 of our difference quotient, which is f of x plus h minus f of x all over h. So I'm going to simplify the difference quotient first. So f of x plus h is 4 over x plus h minus f of x, so minus 4 over x, and then all over h. In order to subtract those, I need a common denominator, so I have to multiply 4 over x by x plus h, and I have to multiply 4 over x plus h by x over x. So that gives me 4x minus 4x minus 4h in my numerator, all over x times x plus h, all over h over 1. That h is not a fraction, so I'm making it a fraction so we can see, right, that we have a fraction divided by a fraction. So simplifying that numerator, the 4x's cancel, so that leaves me with negative 4h over x times x plus h. And instead of dividing by the fraction, we multiply by the reciprocal. So those h's simplify, and we end up with negative 4 over x times x plus h. So now, if we evaluate the limit of that as h approaches 0, we get negative 4 over x times x, because h now has approached 0. So that's negative 4 over x squared. So f prime of x, or the derivative of f of x, is negative 4 over x squared. So today we are going to learn the power rule. So the power rule says that let r be a positive whole number, then the derivative of r to the x is r times x to the power of r minus 1. Here's a big long proof of that. Let's talk about what that's saying. So the power rule says that if I have x to the power of r, then the derivative of x to the power of r is r times x to the power of r minus 1. So you might be looking at 4 over x and saying that's not x to the power of r. But it actually is, because remember, 4 over x I can rewrite as 4 times x to the negative first. So there is my x to the power of r. So r in this case is negative 1. So the derivative is going to be r times x to the power of r minus 1. So negative 1 times 4x to the power of r minus 1, so negative 1 minus 1. And I put those parentheses in a bad spot because it's just the x to that power. Let me rewrite that. Negative 1 times 4x to the r minus 1, so negative 1 minus 1. So we have, again, r times x to the r minus 1. So when we simplify that, we get negative 4x to the negative second, which is negative 4 over x to the second. A lot quicker than doing all of that work. So sketch the function f and its derivative, f prime. So if we look at f, which was 4 over x, if we just make like a quick table, we know that we're going to have a vertical asymptote at x equals 0 because we cannot divide by 0. When I plug in 1, that gives me 4. When I plug in 4, that gives me 1. So it's going to look something like this. When I plug in negative 1, I get out negative 4. When I plug in negative 4, I get out negative 1. So we have f of x looks something like that. F prime of x is negative 4 over x squared. So again, I have a vertical asymptote at x equals 0 because we cannot divide by 0. And again, making a quick table, when I substitute in positive 1, I get out negative 4. When I substitute in 2, I'm going to choose 2 because 2 to the second power is 4. I get out negative 1. And on the other side of my asymptote, when I substitute in negative 1 to the second power is positive 1, so I still get out negative 4. Same thing with negative 2, I get out that positive 4, so my derivative looks like that. And if you look at the function, again, think about what is happening here. So the slope of that tangent line is about 0, and then decreasing the entire time, getting steeper and steeper and steeper and steeper, more negative, more negative, more negative. On the right-hand side, same thing, starting out very, very negative and then getting closer to 0, but still negative. So that is how we end up getting that derivative graph. All right, so let's practice the chain rule. So again, chain rule says that the derivative of x to the power of r is r times x to the power of r minus 1. So 2x to the third is 2 times 3. Drop that 3 down, x to the power of now 3 minus 2. And then we have negative 5. Drop the 2 down, x to the power of 2 minus 1. Plus 7. That x is to the first power, so drop that 1 down, and now we have to the power of 1 minus 1. And for negative 10, that's really negative 10x to the 0th power. So technically what's happening here is we're saying negative 10 times 0, x to the 0 minus 1, but anything times 0 is going to ultimately just end up being 0. So any constant, when we take the derivative, is going to disappear because it's going to end up equaling 0. So when we simplify that, we end up getting 6x to the, put a 2 there, that is a 1. I was one step ahead in my brain. 3 minus 1 is 2. X to the second power minus 10x to the first power plus 7. x to the 0th power, but anything to the 0th power is 1, so that just ends up being 7. So the derivative of f of x is 6x squared minus 10x plus 7. Example 3, 3x to the 4th, drop the 4 down, that's 12x to the decrease that exponent by 1, third, plus drop that negative 2 down, that's negative 8x to the decrease that exponent by 1, so negative third, minus, or plus, drop the 7/4 down, so negative 7/4 x to the decrease that exponent by 1, so 7/4 take away 1, or 4/4 is 3/4, plus 2 square root of x is really 2 times x to the 1/2. So drop that 1/2 down. 2 times 1/2 is 1. X to the 1/2 minus 1 is negative 1/2. So there is the derivative. Notice you do not have to have a polynomial because f of x is not technically a polynomial since we have rational exponents and negative exponents. So anything that fits that form of r, or x to the power of r, or x to the power of anything can be, we could use the power rule for. All right, last example is again an example we've done a few times, but now instead of just having an idea of what the derivative is based off of a graph, we now have a power rule and can find the derivative. Or instead of having to use the definition of the derivative to find the derivative, we have a power rule to find it quickly. So sketch the function f and the derivative. So if I sketch f of x, which is x squared plus 3, that is our parent function x squared shifted up 3 units. So when we are graphing the derivative, we know that we have that negative slope until 0, and then it becomes a positive slope. So it's going to look, something like that. So let's actually find what the derivative is. So using my power rule, if f of x is x to the 2nd plus 3, then f prime of x, drop that exponent down, so that's 2x, and decrease the exponent by 1, so that's to the 1st. And constants, again, go away because anything times 0 is 0. So our derivative is the linear equation, y equals 2x. So find the slope of the tangent line at 1,4. So remember, the derivative is the slope of the tangent line. So if I want to find the instantaneous rate of change, or the slope at a specific x value, all I do is I substitute that x value in. So f prime of x, or f prime of 1, because we're looking for the slope of the tangent line at that specific point, is 2 times 1, which is 2. And find the equation of the tangent line at 1,4. So in order to write an equation of a line, we need two things. We need the slope, which we just found in C, and then we need a point, which was given to us. So since that point is not the y-intercept, I'm going to use point slope form. Y minus y1 equals the slope times the quantity x minus x1, and there you go. And if we look graphically, if we were to look at that quadratic, the x squared f of x, which is x squared plus 3, that original function, x squared plus 3, and we graph this line, which if I were to put that into slope-intercept form, distribute the 2, move the 4 over, it ends up being y equals 2x plus 2. We can see that that ends up being the tangent line at that specific point. All right. I misspoke. I said the last one were our last two examples, but I actually would like us to do examples 5 and example 6, and then we're going to start there. But I would like you to do example 5 and example 6 without me. So go ahead and pause this video, and then once you have your answer, graph it, or play it again, play the video again. All right, let's check our answers. So example 5, between the interval of 0 and 1, our slope is 4. So we have that constant rate of change of 4. So we have a horizontal line at y equals 4. And then between the interval of 1 to 2, we have a constant. So the rate of change is 0. And then between 2 and 4, the rate of change was a constant rate of change of 4 over 2, or 2 over 1. So we end up having that horizontal line at 2. Make sure we have open circles on the ends, because we have an open circle there too, because remember, we are not differentiable at those cusps. And then 6, going the opposite direction, we're graphing now a position function, right, that has a constant rate of change of 5 between 0 and 2, then a constant rate of change of 0 between 2 and 3, and then constant rate of change of 10 between 3 and 4, and that is what that ends up looking like. All right? And we will do the rest of this at a later time. Now that you are done, you can go up and ask the substitute for the homework. Homework is over at the power rule, so practicing problems like example 2 and example 3 a little bit more in depth. All right, have a wonderful weekend. Enjoy your extra days off, and I will see you next week.